So I'd like to introduce Tim Hunter. Tim Hunter is a core engineer on the Spark team, and he's here to talk about the ML piece. Do you want to talk a little bit more about your background here, Tim?
Sure. Can you hear me over there in the back? Okay, perfect. Welcome to this session here. So I'm going to talk to you about MLlib, the machine learning component of Spark. And I've been working on machine learning and Spark since my PhD at UC Berkeley. I think back then it was Spark 0.6. We're not very good at naming the release back then. And now I work as a software engineer at Databricks, working on MLlib. So today I would like to present a bit what you can do with MLlib and how it fits within the Spark environment. And also take a step back and talk a bit about the kind of challenges that we encountered when implementing distributed machine learning algorithms. So this is more for people, the people among you who want to implement these algorithms to see what kind of problems you should be aware of. And finally, I would like to expand a bit what Doug has been talking about and show you how you can use MLlib not only in the case of, how you can use Spark not only for large-scale data sets, but also how it is useful for smaller data set as well. So let me talk briefly about MLlib first. So MLlib is one of the core components of Spark. It was included since Spark 0.8, and nowadays it is it's a very active component within Spark with more than 200 people contributing, having contributed some algorithms to it. And it mostly focuses on distributed algorithms, so making sure that all the algorithms inside scale as well as at the rest of the Spark ecosystem. So MLlib's goal is to make sure that you can run machine learning algorithms in a way that is easy and scalable. So by this I mean that you should be able to use MLlib for most of the problems that you are going to encounter, being classification, regression, clustering, and so on. And that also the output should really be something that you can work with, given and that it should also account for all the idiosyncrasies of real-world data. So whatever you throw at it, it should be able to handle it. And finally, we'll talk more about it later. MLlib includes some tools for dealing with day-to-day workflows, and in particular, how to build pipelines, but also how to integrate with third-party libraries. And of course, as you would expect, it integrates well with the rest of the Spark ecosystem. So you probably cannot read this slide, and this is the whole point. So nowadays, MLlib covers nearly every big domain that you can expect in the Spark. In machine learning, and you can solve some classification tasks, regression. Also, it includes a large number of ways to transform feature vectors, which is pretty convenient for machine learning. And it also includes some libraries for doing basic distributed linear algebra, if you want to really work at a low level like this. And I highlighted in bold, which is something you can probably see, the latest algorithm that we introduced since Spark 1.6 and Spark 2. And I would like mostly to highlight the fact that most of these contributions have been from open source contributors. So this is definitely a big collaborative effort on which people can easily contribute. So that was a brief introduction to MLlib. And in order to implement most of these algorithms, we have to take into account a number of issues that come up not only because we work with big data, but also because we work with large distributed environments. So I'd like to talk today about 3 of these issues that, as a practitioner, you also have to be aware of. The first one is that Doug already mentioned is the iterative nature of this algorithm. The second one is that you can have very different performance depending on how your data is being partitioned across your cluster. And finally, if you implement some algorithms, you have to be aware of the fact that models can really grow to extremely large scales, And this is becoming more and more prevalent nowadays. So if you take algorithms like gradient descent, like we were talking before about, one critical piece to make them work at high performance is to make sure that Spark is aware of the fact that you're going to reuse this data set. This was the caching that we mentioned. Spark includes a number of caching strategies, and MLlib takes these into account when it schedules when it schedules some computations around the cluster. And so if you are working on a very long-running task, one fact that you should be aware of is to make sure that at periodic intervals you can ask Spark to checkpoint the current result so that if some failures happen somewhere, it is able to continue from where it left off instead of restarting from 10 or 20 iterations before. Data partitioning is probably the most relevant when you work with big corpus, especially if you work with algorithms that deal with topic modeling, such as LDA, latent directly allocation. It is very typical for some machine learning algorithms to work really with two sets. For example, in the case of LDA, you have a set of documents on which you can associate some words. And the algorithm behind LDA shuffles some data back and forth between the terms, between the words, the terms, and the document. So depending on how you partition your data set, you may have more or less data being transferred between the machines. And as we'll see afterwards, really the key to achieve good performance for these algorithms is to minimize communication between the machines. So one strategy that the Spark implementation does, and that we'll talk more about, is to make sure that when considering such a graph, all the documents that are pertaining to similar terms are clustered together. And we'll see a more detailed example later with alternating the square. And there is a third issue which is a bit more subtle and that doesn't necessarily come to mind naturally. It's at a high level, it's what kind of algorithm we use and depending on how big your model is. For example, if you consider a small number of features, for example, if you have a small dimension, a few dimensions, then you can simply, in the case of, for example, least square computations, you can compute a covariance matrix, invert it, and you are done, solving the normal equations. If you start to work with, let's say, 100,000 or 1,000,000 features, then storing this covariance matrix is impossible because it takes too much time to just materialize, and also it takes too much time to move around. So then you have to go back to method that for a single machine are deemed to be too slow, but actually makes sense in the context of distributed computing. And for example, doing gradient descent or using a limited memory BFGS would be a good fit in this case. Because for these methods, you can still materialize vectors, you can still use them, shuffle them around, pass them around, and work with them. And then you can, so this is for the vectors of reasonable size. But then you can move to really the truly huge dimensions, which actually come more and more often these days. And in this case, even though the data set might be very sparse, each of the vectors it is used to represent these feature vectors might be in the billions of elements. And in this case, you cannot even usually materialize a single vector for any of these elements. And Spark includes for some algorithms, some versions that can deal with these extremely large feature vectors. So you might think that the first point is well addressed by local libraries. So for example, scikit-learn, R, and so on. Spark is good at the second point when you start to deal with big dimensions. And the third one is really just for Google and Facebook. But when you think about the size of the data set these days that come in the billions or tens of billions of feature points, you can see that people nowadays try to express all the aspects of this data set. And in doing so, they build extremely complicated models that tend nowadays not to fit anymore in one computer. So this is why Spark now starts to move more and more into implementing some of these vector-free algorithms. So let's talk about an example to show you how it makes a difference to think about these problems already from the outset. So I'm going to consider a problem that you have probably been aware of, which is a collaborative filtering, also known as the Netflix challenge or the Amazon challenge. So imagine that you have a number of items, for example, songs, and you have a number of users. And each of the users may rate a subset of these items. For example, this user likes this song, and so on. And we have, so for a number of users, we have some ratings and so on. And what we would like to do is to predict the rating for a song given a user. And so, of course, we could simply present this to the user and see if he or she will like this song, but we can do much better than that. So one way to formalize this problem is to consider that all the ratings form a big matrix with, for each row we have the users, and for each column we have each of the product we would like to rate. And in this matrix we observe some of the entries, not all of them. And one assumption we can do, which is pretty well verified in practice, is to consider that this matrix can be approximated by a low-rank approximation. That is to say, we can associate to each of the users a tiny vector, usually in 10 or 100 dimensions. And we can also associate to each of the songs a small vector in the 10 or 100 dimensions. And each of the ratings we're going to observe will be the dot product of the vector corresponding to the user to the vector corresponding of the item. So if we put some mathematical notation behind it, let's call our big matrix, which can be really huge, but for which we observe only a tiny fraction of the entries, let's call it A. And then let's call the users, the user column vector, column matrix U, and V the items. So you can see how we can approximate with this model each of these entries by doing a dot product between each of the elements. So Aij in this case correspond to one rating for the user I and the song J. So one typical way of trying to solve this problem is to minimize the squared error. And in this case, that corresponds to minimizing the Frobenius norm of the reconstruction. So you can write it, and if you have done some convex optimization before, you know that this problem is not convex, at least in both of the variables. However, we can work around that. So one observation we can do is, if we look at this problem, and if we, for example, fix one of the matrices, for example, U, then this problem becomes a least square problem in V, and vice versa. If we happen to consider that V is fixed, then this is a least square problem in U, in the matrix U. And furthermore, we can also solve this problem for each of the rows of U or each of the rows of V independently. So at that point, we can say, OK, problem solved. All we need to do is to alternate between solving for U and solving for V while keeping the other fixed. And since all the problems can be solved in parallel, we can simply distribute them on the cluster. Well, this is what Spark implemented at the beginning, and we'll see how it goes after that. So let's think just a little bit more about how we can solve each of these problems. So if you want to solve a problem that involves n songs, and for which, for example, n views, and we have these tiny k-dimensional vectors, so we can solve that in O of nk squared. So k can be considered really small, so essentially it's linear with the number of views, the number of entries we have for each user, or the number of entries we have for each song. And furthermore, if we manage somehow to aggregate all these entries together for each of the users or for each of the items on a computer, then we can use all the existing tools that have been developed for a single machine. And in particular, in Spark, we use LAPACK, which is the industry standard for solving a least square problem like this. So this is nice. And the problem is, how are we going to make sure that this works when we have, let's say, 100 billion ratings and tens of millions of users and hundreds of millions of songs? So as I was mentioning before, the main factor that you have to take into account is the cost of communicating between the machines. And in order to make to make this algorithm work, then you need to dramatically reduce it from the more naive implementation. So if we're doing like before, so one way to do it is to do it as I was saying before, which is to simply take all your, so you can take all your observations for all your user matrix, and you could send it across to all the computers, and then you could solve this equation for V, and so on. And then you could take all the vectors corresponding to the items. You could send them to all the computers, and then you could solve them. But doing so would actually be doing much more work in the communication that we need to. So actually, if you look into this communication pattern, then you would have to shuffle around essentially as many entries of your matrix as you would have, as many entries of the ratings matrix, and this number can become really huge. So we can actually, so Spark implements some ways to cut it down, and it's not pretty in the code, but let me explain the high-level idea. And because this is a very standard pattern that you can find in a lot of other algorithms. So really what you want to do here is minimize this communication. So the way you can do that is to look into your matrix A and split it into blocks and try to aggregate into each of these blocks as many observations as you can, as many ratings as you can. And essentially then you can discard all the empty observations. Because of course, some users will rate songs they like, and some others, and they will make clusters of users around that. So the way it works is you can cluster users together, and you can cluster items together, and you can actually use the correspondence that you have between the two based on the ratings to try to find an efficient way to block these. And then when you pass around the user ratings, for example, then you do not need to communicate these to to blocks which do not have these users. And by keeping an index as to which blocks needs to communicate which other block, then you can dramatically reduce the communication costs. And surprisingly, in this case, what you end up doing is taking your data set and caching your data set actually in two different places. So sometimes it might sound surprising, but instead of caching your data set once, I'm trying to say I'm not trying to make copies of my data set. In this case, it is more efficient to actually copy and shuffle your data set in a more optimized way, and then do communication on the users and on the item matrices. So there is, if you want to have more detail about that, there is a whole blog post that explains the gory details on the Databricks website. And how it looks like after that, if you look into what gets scheduled, is a fairly complicated pipeline, which is pretty different from what you would do if you were doing the naive, the more naive approach. So let's see how it behaves. Let's see how it fares compared to the more regular approach. So we ran some experiments taking a set of reviews from Amazon. And so this is fairly tiny, but it gives already a good idea of the scale. So it's 30 million ratings, about 7 million users, and 2 million items. And we run that on a 16-node cluster. So also, for reference, we plotted the same experiment using Mahout, which was a library designed directly using the MapReduce framework and doesn't take into account the iterative nature of the computations. So you can see how Mahout takes already much longer just for running on a tiny data set, just because of the cost of setting up and not knowing that it's going to do multiple passes on the same data. And MLlib 1.2 here, so the red line corresponds to the first simple implementation that we're thinking about, where we're simply sending things around, trying aggregating them on a different node. And you can see that it doesn't scale as well as the approach that I sketched, where we try to be much smarter and more restrictive into what we communicate around. So if you're working on an algorithm, it's easy to start with a simple implementation where you can think about, at a high level, how things get distributed. But usually, if you really care about performance, it pays off to spend more time to optimize for these for your communication patterns. And for that, the Spark UI can help you figuring out what takes some time and how much also data gets shuffled around. And just to give you a sense of whether this is practical or not, and whether it's used in practice, some people at Spotify have used this algorithm to run some experiments. So they had a database of about 50 billion ratings from their users. And they launched a cluster of about 30 nodes. And so it took them about an hour to reconstruct their data to achieve acceptable performance. And the whole experiment cost them about $10 of Amazon credits, which can be, so when you think about it, it's not that expensive. And at the same time, in 1 hour, they could achieve much more than they could ever do with a small cluster that they had set up manually. So, any questions so far? No? Okay. So let me now explain a bit what I think makes MLE particularly useful in practice. And so Doug has already mentioned the pipelines. Some other aspect that I'd like to emphasize a bit on after that is the fact that you can mix and match multiple languages. So if you are comfortable with R or Python, then you can always use this without having to train to some other esoteric language. You have seen the example of Python. But mostly, one point I would like to make here that Spark is not only for big data, as we'll see. So you might be wondering why we have been trying to force you to use this pipeline API before, where we had to set stages and trying to put things together. So there are several reasons for that. It's mainly because we found out from our users that machine learning was better addressed, was usually done in a workflow that was always following more or less the same steps. And it was easier for the users to be able to compose their different steps together when they were making some experiments, especially when they were working on a team. So we tried to follow the scikit-learn API so that you would not have to learn too many new concepts. And also, it integrates with the rest of Spark, especially through DataFrames. So typically, when you have a pipeline, when you try to prototype something, it starts this way. You load some data, you convert it to some numerical features. Google Drive needs to quit. I will not. Oh, can it? Nope, it cannot. Oh well. So yeah, Google Drive is trying to make some features. It failed. So after that, so you can train a model from that, and then you evaluate your model. But this is a theory. In practice, it looks more like this. First, you start to combine multiple data sources, and then you realize that some of these data sources need to be combined together, and then you need to learn some features just for these sources. For example, if you use word2vec or some other unsupervised learning techniques, then you need to already do some pre-processing steps that by themselves already follow pipelines. And then you realize that the final model that you have is not necessarily the best, and you like to evaluate multiple models. And then you like to make an ensemble out of them. So already you can see how it starts to become pretty hairy to put together. And this is where we think that MLE pipelines can help you organize your code, especially when you run it on Spark. And here I would like to talk a bit more about how you can use it also outside. So if you don't have big data, and if you're familiar with scikit-learn, as I think a majority of you are, then you can also use Spark by just changing some of the bits that could make use of a cluster without having to change your existing workflow. So let's say, for the sake of an example, that you want to you extract some features, and you would like to train a model. And this model depends, for example, on the regularization parameter. And you don't know what would be a good value for this regularization parameter. So you would like to try out multiple values, and you're going to find the best one using cross-validation. So here I'm talking about just small amount of data, something you would do locally, something you would not consider using a Spark cluster for. But if you have, here I'm talking about one parameter, but usually you do some search across a grid, or you do some searches using more sophisticated algorithms. So the number of experiments that you need to run can usually increase by very rapidly. And if you use scikit-learn, then you can parallelize onto a single machine, but getting beyond that, using more resources than that can become really tricky. So you can use Spark to take your data set, run some bits of it through scikit-learn, for example, run the parts that can be easily parallelized using Spark, and then get the final result at the end, in all of that in Python. So let me show you a quick demonstration for that. So I have here, can you see, how far can you see? Yeah, at least the first row can see. So here I've loaded some data from this Amazon review set in Spark, and essentially I have some ratings for some items, and then some review corresponding to the item that was being sold. And so the goal would be, for example, here to be able to predict the rating based on the text of the review. So I'm not going to go into too many details on how you would, what would be a good technique for that, but using scikit-learn, you could build a small pipeline in which first you transform your text into vectors, then you transform them to normalize the vectors, and then you would run, for example, a linear classifier on a grid search algorithm in order to find what would be a good parameter for regularization. So here you simply run. So here you'd have to run multiple times the linear regression, and you would try out all these values. So I'm not going to run it here because it takes a while. But what I want mostly to emphasize here is that this is all regular Python code, scikit-learn code. I'm not using Spark in any way here. And if I run it here on this cluster, it takes about a minute to. It took about a minute to run when I ran it half an hour ago. So it takes a while. And all in all, because this needs to run about 20 experiments, but it doesn't know that it can run them in parallel except on the local machine. So just to show you how easy it is to integrate Spark in such pipelines, we have implemented in a small library called Spark sklearn. We have included some replacements for some of the more popular parts of scikit-learn that can be easily parallelized. And for example, here I replaced the grid search algorithm that tries to run cross-validation against a number of values by a version that uses Spark under the hood to distribute these computations. So it is exactly the same code, except for the S here. So essentially, I'm just replacing this element here in a scikit-learn pipeline. So this is your regular scikit-learn pipeline. You don't see that under the hood is going to talk to a cluster, except when you run it, which it should run. Yeah. So and here under the hood, it ran all these 20 experiments in parallel using the cluster I had, and it ran them in 7 seconds. So about, as a data scientist, it means that I could run the same experiment about 10 times faster, just by being able to leveraging the cluster I have under the hood. And this is not big data, but usually it helps a lot to be able to run a lot of these experiments very fast, and Spark can help a lot for doing that. And then, of course, you can continue your analysis, find the best estimator, and then move on to solve the task you have at hand. Any question about that? All right. So if you are a developer, so here I've been talking about more about the development of some of the other algorithms. If you are working on an algorithm that you would like to integrate with Spark, and you would like to get some feedback, one easy way to do that is to package it as a Spark package. There are some tools for doing that on the Spark Packages website. And this lets you use any distribution of Spark and integrate directly within this distribution the coordinate of the package. And then there are a number, but also as a user, you will be interested to see all the other algorithms that are not built inside MLlib, but are available over there. And of course, this being KDD, I cannot resist but showing the number of papers that have been written on MLlib and by Michael here on SQL, and also on graphics. So there are a number of references, one of them actually being presented, I think, today. OK, so this is what I wanted to tell you about MLlib. Do you have any questions? Yes? Sorry, could you repeat your questions? Yeah, OK, so the question was actually a pair of questions. So how to deal with compressing the data to go around, and also how to deal with network errors. So for compressing the data, there are a number of techniques that are used. Mostly, if you use DataFrames, the DataFrame uses their own representation of the data with a compact binary format. And they are much more efficient than what you could achieve by doing it manually. So already, if you use DataFrames or datasets, you get already a performance boost compared to RDDs. After that, you can try to. There are a number of parameters that you can tweak within the Spark configurations. I don't think we're going to cover these parameters, but they're well documented in the Spark documentation. Usually, I would first look into how to change your data structures first, and then look at these parameters later if you're really hitting these issues. So about network errors, well, so I don't have too many good answers for that. I think mostly Michael, do you have something to add?
Yeah, I don't know if there's anything particular to network errors. We do the standard stuff. So the lineage of the RDDs allows us to retry. If you can't get to a specific machine, you can actually just schedule that task somewhere else. Is there like a particular kind of network error you're asking about? So, I mean, it depends on the storage system that you're using underneath. If you're using something like HDFS, it actually keeps 3 replicas of the data on different machines. Spark Scheduler uses a technique called delay scheduling, where what we do is we try to schedule on a machine where the data is located, so you don't have to transfer over that. But if for whatever that delay is, you cannot get a slot on that machine because it's used or because it's unavailable, we'll schedule it somewhere else and then ship the data over to that.
So, let's say you have ingredients on your machine, this is not regular food, the company doesn't have variations, but you have variations of this some things are state, but you need to store in the machine.
Yeah.
So the state is
Yeah, so I mean, maybe it would be better to talk afterwards. This sounds very specific, and we're actually behind schedule, but I would be happy to answer this question afterwards. Any other questions before I go?
Questions? I think there's one over there.
Could you talk about Spark's ability to do deep learning and leverage GPUs?
Sure. So Spark doesn't include right now any built-in facility to use GPUs. It includes some basic algorithms for doing deep learning, such as multi-layer perceptron, but definitely not the state of the art that we see right now. That being said, there are a number of efforts around that because it's definitely a very popular learning technique. So you can use Caffe with Caffe on Spark, a Spark package. For TensorFlow, there is we have been working on an effort called TensorFrames, which integrate TensorFlow and DataFrames, and there are also a number of other packages for doing that. As far as GPU are concerned, Spark doesn't have any notion of the GPU hardware, and usually it is accessed through the other C libraries that directly communicate with the GPU. So this, and what I've seen so far in practice, is that this depends a lot on the deployment of the cluster. So some people, and it is fairly easy to deploy Spark on a cluster of GPU on Amazon, for example, if you don't want to set it up yourself. So if you want, we can talk more about that if you have some more specific questions about that. One last question? Yeah. Oh yeah, so the question is how you compare Python and Scala as far as MLlib is concerned. There used to be some differences in performance. Nowadays, we are trying to use the same underlying Scala implementation for all the algorithms. So unless you happen to have some specific transform that you wrote in Python, all the performance will be the same. When you use PySpark, all you do is calling actually the Java library, the Scala library that does the actual computation.
Yeah, the RDD has like not as good performance when you use PySpark. So is it like same if I use a DataFrame on the MLlib, they will be good. If I use RDD, it will be bad, or?
Yeah, so I agree with you. The performance used to be.
Actually, the topic of the next talk.
All right.
Which maybe we should
So I'm not even going to answer this question because now you're going to have a very long answer to your question. It's all right. So Michael is going to take over to tell you about structured streaming.
Okay. Thank you very much, Tim. So I'm here to talk about structuring Spark, which is really about a bunch of high-level APIs that we've built on top of the low-level RDDs that you've been hearing about today that can actually make it easier to write programs and actually easier to write performant programs. So before, just a little bit about myself. My name is Michael, and I'm one of the original authors of Spark SQL and the Catalyst Optimizer. I'm going to focus kind of exactly on how these systems built on top of Spark can make writing programs easier. So before I dive into structured Spark, I need to kind of take a step back and kind of explain why I think the RDD API is something that I would call unstructured. So you kind of heard a little bit about this in Doug's talk, but just as a reminder, what exactly is an RDD when you write down a computation in the form of an RDD? It's made up of a couple of things. The first thing is a list of dependencies. So this is where am I getting the data from, what RDDs came before this, what blocks are in HDFS, what data is stored in S3, where am I reading the input data from. In addition to those list of dependencies, you also get information about partitions. So this is how do I take that data set that's coming in as the input I'm going to do transformations on, how do I split it up across the cluster into individual pieces? And each one of these partitions has also information about locality. This is what I was talking about in the answer to one of the previous questions about delay scheduling. When we know that data is located on a specific machine, we will attempt to schedule that computation local to where the data is stored to avoid shipping it over the network. And then finally, the last thing is this compute function. And this is actually expressed in an incredibly general way. It is just, I have this partition of data. Now give me an iterator, or something where I can just incrementally produce items from the data set of type T. And all you specify is this function. And the nice thing about this is an incredibly general API. You can express all kinds of computation on top of this. You could build a SQL engine, you could do machine learning, you can do kind of ETL and data transformation. But one problem with this is this computation is actually very opaque to Spark. And it's opaque in two different ways. So first of all, the computation itself is opaque. All I have is this function I'm going to call, and I have no idea about what you're doing inside of that function. It's a black box to me. And that makes it fairly difficult for Spark to optimize. The other thing is the data, the type of the computation that's being returned, that's also opaque. I have no idea if it's a collection of strings, or if it's some integers, or if it's a date. And without that extra information, you as the programmer have to do the optimization yourself. So there's a question about compression and stuff. It's basically up to you as the user of Spark to do that. So on top of this, I come from the database community. And for a long time, we've had this notion of structure. This is what actually SQL stands for, the structured query language. And so when I talk about structure, what I mean is instead of just having this wide open field, this opaque black box to Spark of computation, instead I want to construct and arrange it according to some plan. I want to come up with a set of common operations and express them in a way that Spark actually understands. Oh, I'm adding two integers together, for example. And so the question then is, why would you structure? And so by definition, structure is going to limit the types of computations that can be expressed. If you only have SQL, you can only express things that can be expressed in SQL. But it actually turns out in practice, if you pick the set of primitives that you're going to provide users, you can actually express a wide range of computation, and there's always the escape hatch to go back to RDDs. And really, the key thing that I'm going to try to impress on you in this talk is that by limiting the space of what can be expressed, we enable all kinds of optimizations under the hood where the system can automatically make things smarter. Instead of you saying exactly how you want computation to be performed, you say what computation you want to be done and let the system figure out the fastest way to perform that computation. This is, in the database community, we call this declarative programming. So Spark has a wide range of structured APIs. So kind of at one far end, there's SQL. And with SQL, basically, all you're doing is you're throwing strings of SQL at the system, and it's figuring out how to run them. So there's kind of trade-offs in terms of when you're going to get different programming errors, depending on which of the APIs you're using. But one thing I'm going to talk about is no matter which one you're using, underneath the covers, you're getting exactly the same execution engine. So at one end, there's SQL. These are just strings, and basically like the compiler, if you're writing in Scala or Java, isn't going to tell you anything about mistakes you might make. You have to run your program, and then Spark will say, oh, this SQL string is invalid. One step closer is the DataFrame API. So DataFrames are closer to RDDs. You're actually calling functions on this data set. But underneath the covers, you're doing something very similar to SQL. You're actually assembling a relational query plan that says how the processing should be performed. And then at the far other end of the spectrum, we have this new thing called datasets. And this is going to be the closest to RDDs in terms of what your computation actually ends up looking like. With datasets, you're actually working with objects that live inside of the programming language. And so we can give you compile time safety both for syntax errors as well as analysis errors. For example, if you try to call a field on the object that doesn't exist, the compiler knows the type of that object, and it can actually throw that error for you. But really, no matter what, underneath the covers, Spark is actually able to figure out when errors will occur well before the job actually starts, because we have this whole analysis and compilation pipeline. So I talked a little bit about data sets. I want to go into a little bit more about what it looks like. For users of RDDs, it should actually look pretty familiar. At a high level, basically you can read in data using any of the data source APIs that are available in Spark SQL. So in this example, I'm going to read in a bunch of people JSON. And at this point, I have a data frame. But I don't want to just operate on this as this generic collection of rows. I actually want to get objects that I can do kind of easier programming on top of. So what I can do is I can create a case class. This is written in Scala, but this also works in Java. If you just create Java beans, you can kind of get exactly the same thing here. But I create a case class. I'll say that I'm expecting this JSON data to have two fields. I have a name, which is a string, and an age, which is an integer. So this is already an example of structure of the data. I'm telling Spark what I expect the JSON data to look like, and I'm taking this data frame, which is just a generic collection of objects, and I'm kind of transforming it into this collection of structured objects that the compiler understands now. And so once I've done that, now when I call filter operations, I can actually call lambda functions with the fields of this object. So I can say, filter, I only want things where the age is greater than 30. And it actually knows age is an integer, and so this is a valid type of computation to perform. And now you can even do kind of more complex things. For example, if I wanted to compute a histogram. This would be pretty difficult to express in SQL, but it's pretty easy to express here as a data set operation with kind of functional programming style constructs. So what you're going to see is in all of these structured APIs, really what you're constructing under the covers is the same. It's just different ways of viewing the data based on the type of computation you're trying to perform. So data frames are generic collections of rows. You can think of them a lot like tables that you would see in SQL. And data sets are then specific data frames where I know the exact type of the object. In Spark 2.0, these are actually the same class. So a data frame is really just a data set of generic row objects. And then Spark SQL makes it easy to go back and forth between these. I've been talking a lot about Scala, but I also want to talk about what it's like for Python users, because I assume there's a lot in the audience. And it turns out you've kind of long had a lot of the benefits of these structured APIs in Python because of its dynamically typed nature. So for example, in Scala, before data sets existed, when I wanted to work with these generic objects, it was actually fairly cumbersome. I had to pull out individual fields by their location in ordinal. I had to cast them to a type. And in Python, that's actually always been pretty easy. And so what we're really trying to do is we're just trying to make it easy to express your computation, no matter what it is, using a variety of APIs that fit the specific computation that's being performed. Now, I've said this before, but I really want to emphasize this point because this is actually pretty important. No matter which of the APIs you're using, whether you're writing SQL strings, whether you're using data frames, whether you're using data sets, you're actually getting this whole analysis and optimization pipeline. It doesn't matter which language you're using. And the benefit of this is what's actually figuring out how to perform this computation, taking your data frames, your data sets, your SQL operations, and then mapping them down into low-level APIs. So you can see there's actually a couple of different phases here. The first is analysis. So when you write your computation, the first thing we do is we actually go and we look at the data, we look at the fields, we make sure you're calling fields that are valid, we go and load the table from the database and figure out which columns are available, things like that. Then we perform a whole set of logical optimizations. So a logical optimization is one where we rewrite the query plan. So we rearrange operators or we transform expressions, and we do that without changing the result. So we have a whole bunch of different examples of this where we'll do things like constant folding, we'll rearrange joins to be more efficient, we'll transform outer joins to inner joins when it's not going to change the answer. And so all of these are things that you could do by hand, but the Spark SQL Optimizer can do for you automatically. And then finally, we do something called physical planning. Here you'll notice there's actually a bunch of different boxes, and that's because for any given logical plan, there's actually a bunch of different possible physical implementations that would give you the same answer. And what we do here is we use something called a cost function, where we actually look at the estimated cost of executing each one of those, and we'll pick the cheapest one automatically. And then once we have that cheapest physical plan, we will map that down into low-level RDD operations, just like you could have done yourself, but automatically. So now I've given you the kind of high level. I want to actually dive into some examples where giving Spark more information about the structure of your computation can result in faster, more efficient programs. And so let's start with kind of simple computations. So one example is the column API. So there's a couple of different ways that you can express columns in Spark. So using the DSL, I can say something like column X equals 1. So this is actually constructing an expression that says check to see if column X equals 1. If so, return true, otherwise return false. An equivalent way is to actually pull that individual column out of a data frame. This probably looks more familiar to you if you're a user of Pandas DataFrames. This is kind of an API that we borrowed from there. And then finally, you can actually just express exactly the same thing as pure SQL strings. If I say expr and I give it a string, it'll just use a full SQL parser. So if you're familiar with SQL, anything you can express there can just be dropped into the programming language and will construct the same expression underneath the covers. And then finally, if I really want to, I can actually go all the way out to SQL and express exactly that thing as a full SQL statement. So the nice thing here is these kind of relatively simple things can actually be combined with a whole bunch of built-in computation. So if you're doing standard operations like string manipulation or date and time calculations, math, or even kind of distributed programming things like calculating a monotonically increasing ID across a distributed set of data in an efficient way with minimal network communication, all of these can be expressed with these high-level functions. And so whether I write it in Python or whether I write it in Scala, what's actually going to happen under the covers is unlike a lambda function where you just give it to Spark. Let's say I were to express these same things in Python. That's a black box. Spark doesn't know what's happening, and so it's actually going to have to shell out to Python to say, perform this computation, give me back the answer. If I understand that what you're actually doing under the covers is computing a square root, I can take that and code-gen it inside of the JVM, never go back out to Python, and still give you the same answer, but in a much more efficient way. So a couple more examples here, just kind of giving a side-by-side. Basically, these are completely equivalent in terms of the result that they'll produce, but they'll have wildly different performance. So if you type something like, lambda function of integer x equals 1, what we actually get is this completely opaque class from the JVM. All we know is you have a function that takes an int and it returns a Boolean, but we don't know what you're doing under the covers. If you say column x equals 1, I actually know you're doing equality. And I know all kinds of interesting things about equality where I can optimize the computation. For example, I know that if I hash the values of x and distribute them by partition, all of the ones that equal 1 will be in a single partition. And I can use that to do distributed computing optimizations that you could also do by hand, but you'd have to express that yourself. Another example here is predicate pushdown. So let's say I've got a data set that's stored in Postgres, and I want to load some of it into Spark and do some computation. So one nice thing here, first of all, is when you use these structured APIs, there's a wide array of different connectors just built into Spark. So you don't have to write the low-level code to connect to the database, read the stuff in, convert it from JDBC into objects that you understand. All of that's done kind of automatically. And you can use all of the case class data set magic to transform it into your own domain objects from the database without writing any of the boilerplate code. But even before I do that, I can also do things like add this predicate. So I'll say, where name equals Michael. Because Spark understands what that predicate means, when I actually transmit this query to the database, I can actually rewrite the SQL statement and include that predicate in the database. So results that don't match will never even leave the database, and they won't need to be shipped over the network. This can result in huge performance improvements, and they can be done automatically. And they can even be done transparently. If one person can write the database access code, another person can do an analysis on it, and what the optimizer is doing is actually pushing the filters that the analysis user wrote all the way through down into the actual database connection. Another example here is efficient joins. So this is actually one that I've seen on the Spark mailing list a bunch of times. Someone will write a UDF, so this black box that's doing some sort of comparison to see which tuples should be returned in a join. So in this example, I take two data frames and I join them where the UDF returns true. The problem is I don't know what you're actually doing underneath the covers, and so I actually have to compute a Cartesian product and take every possible pair of tuples between the two different data frames, and then call your function one at a time individually to see what it returns. This is a pretty expensive operation. It blows up computationally kind of ridiculously. If you write exactly the same thing here as a join with a column expression, I actually understand what that equality means. And I know, for example, that values that are equal will hash to the same machine if I do a shuffle. And so instead, I'm going to use a different operator called a sort merge join. And this kind of is done automatically by the optimizer. And this will end up running in n log n time, which is way, way faster than n squared. So that's the computational side of things. But even just in data representation, this structure can also give useful information to Spark. So we have a pretty powerful data model inside of Spark structured APIs. This is actually quite a bit more powerful than what you'd see in like MySQL or Postgres or Oracle, because in addition to all of the kind of first normal form primitive types, we also support complex types. So you can have arrays nested inside of a single row, you can have structures, and then you can also have maps. And these things also compose. You can have structs within structs, you can have arrays of structs. And so what you end up seeing in a lot of use cases is people will kind of create materialized views in their database, where they pre-join things that would have been in separate tables in a traditional relational database. And the reason this is important in a system like Spark is because you're distributed across the machine, bringing that data together can always be significantly more expensive. And now, since we actually understand what the data types are, this is not just an opaque blob of bytes to us. So we can actually do a very efficient encoding of that data. So as an example here, if you want to store the data, 1, 2, 3 Databricks, Spark actually kind of comes up with this relatively efficient encoding, and Reynold's going to talk about this a bunch more in his part of the talk, where we lay this out in binary in a relatively tightly packed way. And because of things like data sets, we can automatically generate the boilerplate code for you to go from that efficient binary representation into your domain objects that you actually want to program against. And that's more than just reading from binary. This is also reading from JSON or reading from JDBC. All of these different connectors can kind of seamlessly do this data transformation for you. And it ends up being significantly more efficient than what your average RDD program would be. So if we look at the space efficiency, this is an example if I take a data set of strings and I just try to cache it in memory. If you use the data set representation with our efficient binary encoding, it's actually significantly smaller in terms of the gigabytes of RAM that you need in order to keep the data set resident in memory than if I were to use pure RDDs. And the performance of actually going back and forth when you're serializing it down into bytes can also be significantly faster. It's kind of long been known in Spark tuning circles that using cryo is significantly faster than using just kind of plain old Java serialization. But it turns out the code-generated encoders that you get inside of data sets are actually significantly faster than even that. And it's even more than just being more efficient when you're going to and from bytes. It turns out when you use these high-level column expressions, we can actually sometimes do the computation without even performing a deserialization. We actually end up operating directly on this binary data. So as an example, if I wrote this DataFrame code where I'm doing a filter, looking for data that came after the year 2015, the parser is going to turn that into this expression where we actually understand you're doing a greater than operation. And then Spark SQL's Cogeneration, which again Reynold's going to talk about a bunch in his talk, will actually produce this stuff that's actually almost at the level of C++ code. This is doing kind of bit twiddling arithmetic, at a low level that actually gets code gen down using something called an intrinsic to something that's pretty much equivalent to doing pointer arithmetic. So this can be very, very fast. So this has just been kind of a high-level example of why structure can be valuable and why it can lead to easier to write faster Spark programs. I want to really quickly go through kind of a toy example of how the optimizer is also extensible. So you as researchers can actually go in and add your own optimizations into Spark SQL and perform computation even faster. So I linked to this from the class sheet. So if you go to the agenda, I've actually added this, this notebook here. So I'm going to go ahead and load this up, if I have internet. Otherwise, maybe we'll cancel the demo. Oh, there we go. OK, so I've loaded this notebook. If you want to follow along, you can actually do this in your own instance of Databricks Community Edition. So I'm going to go over here, and I will just go import and load this URL in. And the URL is in this tutorial document. It's tiny URL. You can type it out. Oh, is it up on the screen somewhere? Tiny URL, Spark KDD 2016. And then you can all take that link. Good. Let me go ahead and I can attach this to. You want to use Spark 2.0 for this. And so let me just walk through kind of really quickly what this example is doing. So this is, like I said, this is a toy example, but it shows the power of injecting custom optimizations into the execution engine. So I'm doing a really simple computation. I am taking a range of integers up to like 1 billion or something, and I have another contiguous range of integers, again, like up to 1 billion, and I want to join them where, you know, the integer from one column equals the integer from the other column. So by default, Spark isn't going to do a particularly fast job of executing this query. It's actually going to produce all billion integers. It's going to shuffle them across the network, and then it's going to perform a join on each one of the partitions. But I bet one of you can come up with a more efficient algorithm for figuring out how many tuples will come out of this, knowing that they are contiguous ranges of integers that are the same. And so it turns out you can actually express that here kind of automatically. So I'm going to go ahead and run this. And what is it? I guess the REPL is initializing. OK, cool. So we ran that, and I can actually run the query now. And so what Spark is doing under the covers is, like I said, it's actually producing all these numbers. It's shuffling them all over the internet. You can see we're actually executing a distributed Spark job. It's broken it down into different partitions. And there we go. And now it's on the other side of the shuffle. So now it's reading all that data from across the network and then doing the individual joins of each one of them. And then finally, there will be a count. It'll bring it down to one partition and calculate the total global number. So, you know, we could actually do this significantly more efficiently if we just calculate the overlap, and we know that that's actually going to be the answer. Like, you know, contiguous integers joined with each other will produce whatever the overlapping range of integers is. So we can just take the start as the max of the two starts, and the end is the min of the two ends, and use that as the result. So what I've done here is I've actually written some code inside the optimizer that recognizes this specific pattern. Take a join where the input are these two ranges, and instead of actually computing it, just replace it with what I know the answer is going to be through static computation. So I will take that and run it. And that injected that into the execution engine. We'll do another run here. And you can see now, instead of actually doing a join, there's actually no shuffle here. It's computing the result without doing a shuffle. And now when I go here and hit run, it finished in less than a second. So just this kind of a toy example again, but this shows the power of the system actually understanding the computation and being able to plug in other optimizations on top of that. So that's the end of my talk. I'm happy to take questions, though, while Reynold sets up, if there are any. Yes? How do you debug in Spark? That's a great question. I mean, so one thing is I do think using these higher level structured APIs, you'll often get better error messages because the system understands the computation. So one piece of advice, which kind of fits the general theme here, is do that. In terms of performance debugging, I usually use the Spark Web UI. I think has a wealth of information. So I would get familiar with all of the different things there. And usually what you're looking for is you're looking for outliers. You want to know, is one task making me go slower, and then you got to figure out what that task is doing. Yes?
Yeah, so my question is about nested structure, arrays of structs within an object. Mm-hmm. Are there good code generation ways to analyze within the structure of a nested thing? So for instance, I put an example on the Google Doc. Where
I think I actually read that question.
Yeah, okay.
I mean, so the typical patterns I see when working with nested data or with arrays of nested data, there's a couple of tricks kind of that are actually built in. So one thing is, if you have an array of structures and you just call into it like you would with a single item, we kind of seamlessly do a map. So if I have an array of people and I take people.name, I will now have an array of names instead. So So that's kind of one trick for working with it. But really, usually what you're trying to do if you want to get really good performance is you do end up doing an explode operation, which exists both in SQL and also in the DataFrame API, so that you get it down to some flat structure that you can then aggregate over. Yeah, so I mean, usually we're doing that with aggregation. I could look at your specific example maybe after this and provide better advice.
There's a question about debugging. One thing you can also do is if you're just running, for example, Scala or Java, you could attach a just normal standard Java debugger to the whole program.
Can you guys hear me okay? The back? Good, all right. Okay, so I'll be talking about more of the physical execution engine part of Spark. And this is, actually Michael already seeded some of the stuff I'm going to be talking about. And a lot of it really comes from the fact that with the DataFrame API and the dataset API, Spark now understands a lot more of the structure of the computation. As a result, there's more room for optimization. And so before we do that, let's take a look at how the hardware trends have been progressing along 3 different dimensions in the last, say, 6 years. In 2010, when Spark project was first started as an academic project, the role was mostly running sort of spinning disks. And they were getting about like 50 megabytes per second out of each of the spinning disks you can get. And now we're predominantly 1 gigabyte. Gigabit networks, and then CPU are running about 3 gigahertz per second per core. Fast forward 6 years, we are seeing sort of ubiquitous SSD deployments everywhere. As a matter of fact, on, for example, Amazon and Google, it's actually pretty difficult to find an instance type that doesn't have SSDs. Each of the SSDs can pump out an order of magnitude higher throughput than what you get in 2010 from spinning disks. And networks getting also about an order of magnitude faster. As a matter of fact, I think a lot of the cloud providers now even experimenting with 20 or 40 gig networks. CPU, on the other hand, hasn't changed that much. We are getting more cores, but the per core, I would say, frequency hasn't really improved that much since 2010. And on the software side, actually a lot of work initially, when you look at big data compute systems, they are looking, sort of focusing on reducing the kind of I/O you would actually exploit. For example, Spark has spent a lot of work actually working on I/O with various kind of scheduling techniques to reduce communication. And at the same time, data formats have improved substantially between 2010 and 2016. If you read the academic papers coming out of 2010, most of the papers using CSV as file formats. And you have terabytes of CSV files that you're doing benchmarking on. But so lately, at least around 2016, Parquet and ORC are sort of this very dense column formats that makes it much easier to actually suck out a large amount of data in a smaller amount of space out of I/O. So as we were benchmarking the sort of Spark application performance, we started to realize about a year or 2 ago that majority of bottlenecks are actually on CPU, on compute, no longer on I/O, so networks or disks. And we actually expect this trend to continue. So we started this project called Tungsten last year that aims at actually improving the memory and CPU utilization of Spark applications, and want to actually make Spark closer to be able to leverage what the underlying hardware is offering. So one thing is this talk focuses exclusively on execution, not on optimization, right? And optimization actually is Michael, I think, just talked to you about. You could actually do, at the query optimizer level, very clever tricks that can actually arbitrarily speed up your performance, but it's actually much harder to do it at the physical execution layer. So we separated sort of Tungsten into 2 different phases. The first phase is what we call the foundation phase, which focus a lot on memory management, cogeneration, and actually cache-aware algorithms. I'm not going to be talking a lot about this, but part of it is so what Michael already hinted at. How do you actually marshal large amount of Java objects in memory, but represent it in a very compact byte form, so we can work around sort of a problem of Java garbage collection. I'm going to focus more on the second phase, which is what's largely accomplished in Spark 2.0. called whole stage cogeneration. So I'm going to just go through this and just phase 2. So about 6 months or 7 months ago, we started Spark 2.0 and planning the development of it. And then we asked ourselves one question, which is, can we try speed up Spark's common operations by an order of magnitude? So Spark's known to be reasonably fast, but can we make it 10 times faster? So in order to do this, there are different ways when you want to do performance optimizations. One way is to hook up a profiler, and you measure what the hot code paths are, and you optimize those hot code paths. But that would actually be fairly difficult to do if you want an order of magnitude performance improvement, because you have to find 90% of the time they are spent and eliminate all that's 90% in order to accomplish a 10x improvement. And it becomes even harder if you want to push this, for example, to 100x, because you need to find 99% of the time that's spent and eliminate all of them. So instead, we decided to actually look bottom up to think about how fast things should really run in a distributed setting, or actually even just in some computation setting. So to do this, let's take a look at one query. And this query is very simple. I wrote it in SQL so everybody will understand it in no time. It's really just scanning some data, matching a filter, and then counting how many records actually matches that filter. All right. So if you take a look how a system will actually compute this query, it typically breaks it down to some sort of query plan. And there's 4 sort of query nodes in this case. There's a scan node, which is responsible for just scanning data, reading data from I/O. And then there's a filter node, which filters data. And there's a project node, which marshals the data into the form that your aggregate operator can actually operate on. And then there's final aggregate node. It's very standard, so that if you run it explain in MySQL, Postgres, or Spark, you'll see something like this. So before Spark 2.0, the internal execution engine for Spark, SQL, and DataFrames, and also the RDD API follows this what I would call the volcano iterator model. And what this model does is it essentially treats each of the query operator as a single sort of iterator, an instance of an iterator. An iterator has a very standard interface. Each systems might have slightly different interfaces, but it's fairly standard. Basically have typically 2 functions. One to tell you when to stop, and another one to just tell you what the current data is. And Volcano Iterator model is actually named after a well-known system called Volcano. I think it was written in the 80s. It's basically standardized the way database internals are built for physical execution. And this is essentially now becoming the standard. If you peek into most of the relational database system, that's how they implement it. It was how Spark RDDs were initially implemented too, and it's how Spark SQL was initially implemented. So there's actually some downsides to this Volcano iterator model of parsing. The upside is it's actually very composable, because all you're having is just a bunch of iterators that need to implement 2 functions. But there's some downsides. One is there's a lot of function call. And the second is there's a lot of memory access. And last but not least, you can't really take advantage of modern CPU features. Now, let's take a look at function call. So just imagine each of this box is an iterator. In order for a box aggregate to actually get a result from its parent, you have to call the next method of the project. And project have to call the next method of filter. And the filter needs to call the next method of scan. So at the very least, you're invoking sort of the next method 3 times here. In reality, it's actually happening a lot more. But for the sake of discussion, so you're seeing 3 here. And then the second is, when you're actually passing the result from one operator to another via this next function call, this is just standard function invocation in the computer system. You have to actually put the data in memory. It is possible the CPU L1 or L2 or L3 level cache can actually cache it and put it in the sort of memory hierarchy closer to the CPU. We have to put this data in memory. And last is you actually can't take advantage of modern techniques like SIMD and all of this, because the compilers are not very good at optimizing iterator code. So instead, we asked ourselves the question, what if we just hire some sort of newbie that just learned programming and ask them, somebody who learned Java in one class, and ask them to write this program? How would they actually implement this query? So we did that. It was pretty simple. There's not a lot you can innovate here if you don't know much about programming. You write something that's similar to this, which is you have a for loop, you're reading your data in from this, put it in memory, you have a for loop to traverse it, and then you have an if to do your filter, and then you would be incrementing a count. Right. This is fairly simple. Now, the question is, if you pit the two against each other, on one hand, you have a simple sort of a 10-minute code written by some programming newbie. And on the other hand, you have sort of state-of-the-art query processing techniques, basically standard in database systems. How do the two compare? So we did an experiment on just a laptop running in a single thread, Spark, against 10 minutes of like 5 lines of code. What we found was when you run in Spark, which follows a volcano model, we really just processing one column, one integer column. It was able to process 14 million rows per second on a laptop on a single core, with data is originating from disk. And the simple code people wrote, the newbie wrote, which has only 5 or 6 lines, we're able to process almost an order of magnitude higher throughput, over 100 million rows per second. So what's going on? How does this simple code written by a student that just learned programming beat actually, I would say, decades of research? So I already told you sort of the downsides of the volcano iterated model. And as a matter of fact, almost all the downsides don't exist in the simple code here. The 5 lines of simple code does not have a single function call in it. Show you again. There's not a single function call in this one. It's just a for loop followed by an if, followed by incrementing some counter. And it turns out function calls are actually one of the most expensive operations in modern data processing. Majority of the world's data, I can bet you, majority of the CPU cycles in this world are wasted in making function calls, at least when it comes to data processing. The second is, in the volcano case, for every time the operator needs to call sort of the next and pass the data around, it needs to put it into the cache or memory. Whereas in the handwritten code, actually all the data are really just in CPU registers, and especially this count variable. It's just the compiler will just optimize it, put it in the CPU register, and then really what we're doing is just incrementing the CPU register. And last, with a simple loop, compilers are actually really good at optimizing that. For example, even the JVM compilers, JIT, can actually unroll the loop, would actually apply SIMD operations in certain cases. But really, we're getting this all speed up with this simple code because the person that are writing it knows exactly what the query is trying to accomplish. Spark was built, or other database system were built as a general purpose execution engine. It's aimed for composability. So the query engine is designed, the iterated model, to be composable. Whereas that simple code was written with the mind to actually solve exactly one purpose, which is the purpose of that query. So the idea of whole stage code generation, which is one of the big efforts we undertook in Spark 2.0, is to exactly take this idea of simple code actually works when you have simple code written for a specific purpose. And rather than treating Spark as a database query engine, you actually treat Spark as a compiler. And you have a compiler that actually generates the code for the entire query plan. That's why we're calling it whole stage code generation, because for each of this pipelinable stage in the query plan, you would actually generate a single function that executes all of it. Now, we didn't invent this. There's actually a VLDB paper in 2011 by Thomas Newman called Efficiently Compiling Efficient Query Plans for Modern Hardware. But Spark is actually putting this into production. So as an example, given sort of a query, there are cases that we cannot, for example, fuse. And this includes examples such as network communication. You cannot have a single function that will actually handle network communication because you need to actually send data to other nodes. But if you just take a generic query plan, typically Spark will be able to collapse a large query into multiple different stages. The typical sort of blocking boundary between stages. In this case, it's like a broadcast join. So broadcast join, the broadcast step itself is something that you cannot fuse. You separate a query into multiple stages. In the case of the original query I gave you, so you have this actually a query plan, and I color labeled it. You actually generate a code that looks, or Spark would actually generate a code that looks basically similar to what you see there. And so I'm not going to do that demo in this slide. It's actually probably difficult for people to tell at the end. But so we actually measure the performance of the different primitives that's in Spark 1.6 versus Spark 2.0. And in Spark 1.6, this is essentially running using the Volcano iterator model, and Spark 2.0 is running with the whole stage cogeneration. And a lot of operations are getting sort of an order of magnitude speed up by this. Now, there's one case there, like for example, sort merge join. We're basically benchmarking the number of nanoseconds you would take to process each row. And in there, you can see in Spark 1.6 is 750 nanoseconds. In Spark 2.0 is 700 nanoseconds. So not a lot of improvement. This is actually to give you a counter example of not everything can be solved by just pipelining and fusing everything. Because there are some operators that are fundamentally more expensive. It takes more time to optimize. So this is sort of one example of, so in the data warehouse role, very typical benchmarks TPCDS. And this is just comparing TPCDS results from Spark 1.6 versus 2.0. Just to summarize the talk, so this new tungsten execution engine is largely complete in Spark. The phase one of it goes a lot into sort of memory optimizations to work around sort of the inefficiencies of the JVM platform, trying to pack as many objects as possible actually into bytes in memory that's managed explicitly by Spark itself rather than by the JVM GC. And the phase two works on sort of whole stage cogeneration. And there's some other thing that's happening I don't have enough time to talk to you about that's getting Spark to be actually a lot faster. All right, that's a very quick short talk. Let me know if there are any questions. Yeah. In the benchmark DB, you mean sort merge join in specific? It's possible. We didn't dig into the part of it. Also, we didn't actually try optimize sort merge join as much, so it's harder to say exactly what's going on. All right. We'll be around for there. 1 minute last. Yeah, so we haven't done a direct comparison recently, but my understanding is we have probably the fastest parquet decoder now on Earth. We probably also have the fastest way you could actually process any of these primitives. So I'd be surprised if Impala is faster. Yeah. All right. Okay, thanks a lot. We'll be around for questions if you have any.